In this video, I'll be sharing to you how to solve rational inequalities. But before we begin, let us have a short formative test. You just have to say whether the statement given is true or false. Let's begin. Number 1. Number 2. Number 3. Number 4. Finally, number 5. So let's check your answer. For number 1, 2 is less than 3 is true. Number 2, it is of course true. It's because we have this symbol or equal to the bar below. Next, 0 is greater than 3/4 is false. Number 4, it's of course true. 1/2 is indeed less than 3/4. And number 5, -6 less than -1 is true. How many correct answers did you get? Oh, that's great. Now, for the inequality symbols, we are familiar with this. We have the symbol less than, greater than, less than or equal to, greater than or equal to, and unequal. So I hope that you do not interchange less than from greater than. For our exercises today, we need to solve the following rational inequalities. We have 2 items. So let's start with the first number. As we solve the rational inequalities, we will be following these 4 important steps. Step A. Rewrite the inequality as a single rational expression on one side of the inequality symbol and 0 on the other side. So in this case, 2x over x plus 1 greater than or equal to 1 will be changed like this. Positive 1 will be transposed to the other side of the inequality, and since this is positive, on the other side it becomes negative. Using the concept of LCD, so we have this quantity 2x minus 1 times x plus 1 over quantity x plus 1. Where did we get x plus 1? It's because the LCD of these 2 expressions is quantity x plus 1. Since this is already x plus 1, just have to write 2x. And here, copy first minus 1, and then we all know that the denominator when the number is whole number is of course 1. So x plus 1 over 1 is x plus 1. That's why there is a need to multiply x plus 1 here. Next is to simplify. So -1 times x is of course -x. -1 times +1 is -1. And then 2x minus x is x. And then copy -1 all over quantity x plus 1 greater than or equal to 0. And this is already our single rational expression wherein 0 is indeed on the other side of the inequality. For step B, locate the x values for which the rational expression is 0 or undefined. Take note the values which can make the expression 0 or undefined, after which we mark the numbers on a number line, and then we use a shaded circle to indicate that the value is included in the solution set, and a hollow circle to indicate that the value is excluded. So how do we find the values for which the expression is 0 or undefined? Simple. We just need to equate the expression in the numerator and in the denominator to 0. So for the numerator, we have here x minus 1 equals 0. Therefore, x equals 1. 1 is the value for which the rational expression is 0. For our denominator, we have x plus 1 equals 0. Therefore, x equals -1. So again, negative 1 is the value for which the rational expression is undefined. Since we have identified the values of x, we now create a number line. In our number line, we use the shaded circle because this indicates that the value 1 is included in the solution set, whereas the value negative 1 is not included. Why? It's because when we substitute positive 1 to our rational inequality, it's like this: 1 minus 1 over 1 plus 1. 1 minus 1 is 0, and 1 plus 1 is 2. 0 over 2 is 0, and 0 greater than or equal to 0 is still true. That is why 1 is included in the solution, and we use the shaded circle. Negative 1 is not included. It's because it can make the expression undefined. Any numbers that can make the expression undefined is not part of the solution. Another hint: when to use a hollow circle and a shaded circle. When the inequality symbol used is like this, greater than or equal to and less than or equal to, all the values of x for which the rational expression is 0. Take note, 0. It is part of the solution. Again, when using these inequality symbols, all values of x for which the rational expression is 0 is part of the solution. So we use a shaded circle. When the symbols used is just greater than or less than, no need to shade it. It's because those numbers, whether it can make the expression 0 and of course undefined, they are not part of the solution. So moving on. Third step is to select a test point within the interior of each interval and then construct a table of signs. What is a table of sign? It looks like this. We have the intervals, the test points, and then these are expressions found in our single rational expression. You may ask, where did I get these intervals? If we try to look back in our second step, we have this number line. And if you would see, the circles here divide the number line into 3 intervals. What are these? So we have here the first interval, the second interval, and the third interval. In our first interval, x less than negative 1, or from negative infinity to negative 1. In our second interval, we have negative 1 less than x less than 1. And in our third interval, we have x greater than or equal to 1. Again, since the inequality symbol used is greater than or equal to, our circle here is shaded. So let's go back to our table of signs. Now for our test point, make sure that these test points are within the interior of each interval. So from negative infinity to negative 1, negative 2 is, of course, within that interval. From negative 1 to positive 1, 0 is the most appropriate. And for x greater than or equal to 1, of course, 2 is also appropriate. So you can use any numbers, just make sure that these numbers are within the interior of each interval. So now let's begin. The idea here is to replace the test points in all the x's found in the first column. Why is this negative? It's because when we substitute negative 2 minus 1, it's negative 3. Therefore, the sign is negative. Next, negative 2 plus 1 is negative 1. Therefore, the sign is negative. So, for the sign here, since this is a ratio between quantity x minus 1 and quantity x plus 1, negative divided by negative is of course positive. In our next test point, 0. 0 minus 1 is negative 1, so therefore it is negative. 0 plus 1 is positive. Negative over positive is negative. Next, 2 minus 1 is positive. 2 plus 1 is positive 3, therefore this is positive. And positive over positive is positive. Now we'll look for the intervals for which the rational expression is positive. Why? It's because of the symbol greater than or equal to. And this interval is found in these two: x less than negative 1 and x greater than or equal to positive 1. Now our final step, summarize the intervals containing the solution. The graph of the solution set is here, the one in a shaded portion. Thus, the solution of the given rational inequality is the set x is an element of real numbers such that x is less than negative 1 or x is greater than or equal to positive 1. This can also be written as parenthesis negative infinity negative 1 union with, we need to use the bracket. Here it's because 1 is included, and then positive infinity. And that is the answer for exercise 1. It's quite long, right? However, if we follow the steps, then we can surely attain the correct answer. Let's move on with exercise 2. So exercise 2 is 3 over x minus 2 minus quantity 1 over x less than 0. Again, the first step is to rewrite the inequality as a single rational expression. Now in this case, we need to find the LCD. The LCD between these two quantities is x times quantity x minus 2. So how did we get this? Our LCD, which is quantity x times x minus 2 divided by x minus 2, is of course x, and then times 3. That's why we have here 3x. And then our LCD divided by our denominator here, which is x, the remaining is x minus 2, and then multiply it to 1. So that's why we have it here. Okay, now continue. Negative 1 times x is negative x. Negative 1 times negative 2 is positive 2. So moving on, 3x minus x is 2x. And then copy 2. All over quantity x times quantity x minus 2 less than 0. So we have here our final single rational expression. We have 2 times quantity x plus 1, so we factor out 2 all over x times quantity x minus 2 less than 0. For our second step, we need to locate the values of x wherein the rational expression will be 0 and undefined. So to do that, let us equate the quantity found in the numerator and in the denominator to 0. So in our numerator, we have x plus 1 equals 0. Therefore, x equals negative 1. For our denominator, we have two values of x. We have x here equals 0 since we have this quantity, and x minus 2 equals 0. Therefore, x equals positive 2. We are all using unshaded or hollow circles. It's because negative 1, 0, and 2 are not part of the solutions. Take note as well of the inequality symbol used. It's just less than. No equal to here. That's why we will all be using hollow circles, even though negative 1 can make the rational expression 0. Now in our third step, select a test point. But first, let us identify how many intervals are there. So going back, as you can see, the number line is divided into 4 intervals. We have here the first interval, the second interval, the third interval, and the fourth interval. So our first interval is x less than -1. Our second interval is in between -1 and 0. Our third interval is in between 0 and 2. And our third interval is x greater than 2. So we have 4 intervals. Now, on our table of signs, we have here our test points. Let's check whether the test points are within the interior of each interval. So is -2 within this interval? Yes. Is -1/2 within the interval -1 and 0? Yes. We can also use -1/3, -1/4. It depends on you. What about 1? Is it within the interval 0 and 2? Yes. And for x greater than 2, we will be using the test point 3. So let's begin with our signs. Here it's negative. It's because -2 plus 1 is -1 times 2, it's -2, so it's negative. When x is -2, it's negative. Then -2 minus 2 is -4, it's also negative. For our sign here, since this is multiplication, so negative times negative is positive. And then for our sign here, we have to divide the sign in our numerator and the sign in our denominator. So negative over positive is negative. Next, our second test point, -1/2. So replace it in our expressions here. So -1/2 plus 1 is positive, and positive times positive is positive. X is -1/2, therefore it's negative. -1/2 minus 2 is, of course, negative. And then negative times negative is positive. And then for our sign here, so positive over positive is positive. Next, in our third test point, +1. So 1 plus 1 is 2. Times 2 is 4, it is positive. When x is 1, of course it is positive. 1 minus 2 is negative, so it is negative. Here, positive times negative, it's negative. And then for our sign here, positive over negative is negative. Finally, for our last test point, we have 3. So again, replace 3 in all our x's here. So 3 plus 1 is 4 times 2 is 8. It's positive. X equals 3 is positive. 3 minus 2 is 1, so it's positive. Positive times positive is positive. And then for our sign here, divide the two signs. We have our numerator, which is positive. Our denominator is positive. Of course, it is positive. Now the question is, are we looking for the intervals for which the expression is positive or negative? It's negative. Why? It's because we are using the inequality symbol less than. When we have here negative, of course, the expression here is true. When we use positive, when positive is less than 0, it's already false. That's why we will be looking for intervals for which the expression is negative. And so it is found in these intervals: x less than -1 and 0 less than x less than 2. So for our last step, we summarize the intervals containing the solution. The graph of the solution set is found in here. Thus, the solution of the given rational inequality is the set x is an element of real numbers such that x is less than -1 or 0 is less than x less than 2. We can also write this as negative infinity to negative 1 union with 0 to 2. We did not use bracket because 0 and 2 are not part of the solution. So with negative 1, that's why we are all using here parentheses. I hope this lesson helps you in solving rational inequalities. Stay tuned for our next lesson.